Okay, so now we are going to discuss how the fluidization of the bed, or the velocity of the flow affects the properties of the bed, mainly the pressure drop and the porosity. So for this first graph that we see here, it's a relation between the fluid velocity and the pressure drop. And you see here this dotted line splits the graph into two regions, the static bed and the boiling bed. So static bed is the fixed bed. So the particles maintain their place. They are not changing their place with the increase in the velocity. So as the velocity increases, you'd see the pressure drop is increasing linearly, and this assumes a laminar flow. So the pressure drop is linearly dependent on the velocity. And you see here the slope is high, so with any change in the velocity, it will lead to significant change in the pressure drop. So this will keep going until we reach point A, where the bed starts to fluidize. So this part is kind of a transitional part between the fixed bed and the fluidized bed. So I'll discuss this in some details in the next slide, but for now let's just agree that what we have here is the beginning of fluidization. What is important here is this line. So this line represents the pressure drop change with the velocity. And with a very simple comparison between the slope here and the slope here, you can easily tell that the operation, or you can understand why we say that the fluidized bed is more flexible in operation than the fixed bed. We said that it's a specific change in the velocity. Let's say increasing the velocity by 1 meter per second in case of static bed will lead to a big change in the pressure drop. While here, because of the very small slope here, the big change in the velocity will lead to a very small change in the pressure drop, which means that you can still operate the same column with different velocities, and the pressure drop is going to be around the same value. It's not going to change a lot compared to what we have in the static bed. And this is why the fluidized beds are more flexible in operation than the fixed bed. Of course, the pressure drop here is higher because the velocity is much higher than the velocity here, which leads to more pressure drop, of course. This is what we know from before. But we are here concerned with the flexibility of operation, not just the value of the pressure drop. So this is the first thing. Now we will keep increasing the velocity until we reach point C, which is called or referred to as the entrainment point. Entrainment means that the velocity of the fluid is high enough to overcome the gravity, and it's not only this, it's high enough to take the solid particles with it while it's leaving. So it's simply like the vacuum cleaner. So the vacuum cleaner is what it does. It sucks air with very high velocity, and this air drags the solid particles with it while it's flowing inside the vacuum cleaner. So it's the same thing. We have the solid particles moving, or the air velocity is high, is getting high and higher until it reaches the point it's not only fluidizing the bed, it's also taking the fluid particles with it to the other part. So this is not what we are interested in now. This is, there are other types of beds that are called moving beds that operate in this region, but for the fluidized beds we operate within this velocity range. Now let's try to understand this part. So for this part, we have to understand that we have this graph between the velocity profile of fluid velocity like this, but here we have the bed porosity. So we are seeing how the porosity of the bed changes with the velocity. So again, we are just to understand what happens here, we have the velocity increasing starting from 0 and going up, and as it goes in this static bed region, it's the fixed bed, so the particles are not changing in place, and they are maintaining their spaces between them, and this is why we call it a static bed. So until this point, the porosity is not changing. Now when the velocity increases and reaches the point where the fluidization starts, it doesn't go from 0 to 1. meaning that it's not from static bed suddenly to a totally fluidized bed. It happens gradually. And what happens is that part of the bed starts this way. We call it batch fluidization, because part of the bed is fluidized, while the rest of the bed is not. And as we increase the velocity more, another part starts to fluidize, and then with increasing the velocity more, another part starts to fluidize. So there are different random parts that will fluidize. And as of course as each part increases, or the more parts are fluidized, we'll have more porosity, of course, because there's more space. So this is why the porosity increases from the onset of fluidization until the point where the whole bed is fluidized. Once the whole bed is fluidized, the porosity stays constant, and this is what we call the continuous fluidization. Okay, so this transitional region is is what corresponds to this region here. Okay, so this is the effect of the fluid velocity on the bed porosity. The velocity at which the fluidization starts, this is what we call the which is the minimum fluidization velocity. And this is what we will be focusing on starting next video, inshallah. So I'll see you then. Goodbye.